Okay, picture this. You're walking into a crime scene, but it's not a normal room. It is 100,000 light years across. The evidence is 11 billion years old, and literally everything has been spinning, mixing, and completely scrambling since the event went down. Sounds impossible, right? Well, that is the exact challenge of understanding our very own Milky Way galaxy. Today, we're going to look at how two astrophysicists just managed to crack this ancient, deeply compromised cosmic cold case. The team that finally solved this is spearheaded by lead authors Matthew D.A. Ortney and Chervin F.P. Laporte. They just dropped a massive paper in the monthly notices of the Royal Astronomical Society, dramatically titled Build-Up and Survival of the Disk. And I'm talking about this like breaking news because it really is. They have definitively answered a huge, lingering question about the incredibly violent history of our galactic home. This research is making waves right now, because it finally explains why our galaxy looks like this beautiful, structured, spinning disk today, rather than just a chaotic, disorganized blob of dead stars. So what's the actual catch here? I mean, how do you even begin to solve a cosmic hit and run that happened 11 billion years ago? The fundamental issue the researchers were up against is that observing the early Milky Way is notoriously difficult. Billions of years of cosmic history, stars being born, dying out, constantly shifting around, have totally scrambled the physical evidence. You can't just point a telescope at a star today and easily figure out exactly where it was born or what violently bumped into it eons ago. To really grasp what happened, let's set the stage. Right before the crash, we basically have two main characters on our cosmic detective board. First up, we have Aurora. This is the original, beautiful infant protodisk of our Milky Way. It was young, and crucially, it was spinning. Then we have the incoming threat, GSE. That stands for Gaia, Sausage, and Enceladus. This was an entirely separate, rogue dwarf galaxy, and it was hurtling on a direct, unavoidable collision course with Aurora. Boom. When GSE finally slammed head-on into our young galaxy, the massive impact kicked up an unimaginable mess of stars. The researchers literally called this debris the splash because of just how incredibly violent this mixing was. The original infant Milky Way stars and these violently kicked-up splash stars have become almost totally indistinguishable from each other today. If you map them out, they just look like a massive, scattered funnel of debris. Which leads us to the core mystery of the whole paper. Just how bad was this crash? Astrophysicists were totally split between two competing theories. Was it a major merger, meaning a catastrophic galaxy-destroying collision that would have completely wiped out and scrambled all the rotation of our early galaxy? Or was it a minor merger, a violent, yes, but ultimately survivable impact that would leave some of that original stellar rotation intact? To find the truth, the team knew they needed a totally new forensic approach. To crack this, the researchers brought in the heavy machinery. They used highly advanced supercomputer simulations of galaxies colliding, and then matched those simulations up with actual present-day data from the Gaia Space Telescope. By comparing these simulated crashes against the real-time movements of our stars today, they could forensically reconstruct the past. They were basically tracking exactly how the galactic disk gained and managed to retain its rotational momentum over billions of years. And right here, this is the pivotal clue. The data revealed that ancient stars, and we're talking about stars that are a staggering 13.5 billion years old, well predating the collision, these stars are actually still rotating strongly today. Think about that. If the collision had been a catastrophic major merger, those ancient stars would have been knocked completely out of their orbits. The fact that they survived and kept spinning directly limits the maximum size of the incoming galaxy. Which brings us to the climax of the investigation, the hard numbers. Because those ancient stars survived and held on to their spin, the researchers mathematically proved the mass ratio of the collision had to be less than 1:4. This is huge. It officially rules out a major merger. The GSC impact was definitively a minor merger. Yes, it battered our young galaxy, and yeah, it created that massive splash, but it did not destroy our galaxy's fundamental spinning disk. But you know, the researchers didn't stop there. They wanted the exact time of the interaction. By tracking a very sudden, specific drop-off of certain stars located in the galactic halo, they managed to pinpoint the exact moment the incoming galaxy made its first devastating strike. It happened precisely 11 billion years ago. So let's look at the full timeline they established. 13.5 billion years ago, the beautiful Aurora protodisk forms. Fast forward a bit, and 11 billion years ago, the GSE impact hits us. But here is the really wild twist. The shock waves from this incredible collision didn't just scramble existing stars. They directly triggered an intense, massive burst of brand new star formation. And that burst essentially created the mixed galactic disk that you and I reside in today. Now, you might be asking, how confident are we in this result? Honestly, very. Because they found a brilliant smoking gun. The exact timeline of the GSE collision in their computer simulations perfectly matches the age and chemical makeup of real globular clusters, these dense, ancient groups of stars that were formed during that exact massive starburst. The simulated mass data from the splash lines lines up flawlessly with the actual, real-world star distributions we observe. It's a remarkable piece of independent corroboration that proves their 11 billion-year timeline is right on the money. Of course, like any good detective story, there are always a few cold cases left open. The researchers are completely upfront about the limitations we still face. Right now, our stellar age estimates still lack the sub-percent precision we'd really need to get a flawless, high-definition picture of the early galaxy. Plus, we can only measure how stars are moving from our current vantage point today. So the very, very earliest conditions of the proto-galaxy, those are still largely hiding in the shadows. But man, this brings us to an incredibly exciting future. What are next-generation space telescopes, like the upcoming Plato mission, finally going to reveal about our violent cosmic history? As these completely new eyes in the sky start giving us unprecedented precision on stellar ages, we are going to be able to peel back even more layers of this 11 billion-year-old mystery. Our galaxy survived its absolute greatest impact, but it left scars we are only just now beginning to read. So it makes you wonder, what other secrets are hiding right above our heads?